Okay, Eric, this is question 15 from that sample test that you had. And this, again, deals with the fundamental theorem of the calculus, um, the second fundamental theorem of the calculus. Uh, and we mentioned that in the video for 14. So again, you're doing a rate of change of an area, right? And this one's a little more complicated because both bounds are variables. And so the technique is to split it up into two integrals, which will have one of the bounds in each of those integrals be a constant. So what we basically do, the rewrite is going to look something like this. It's going to be the integral um, from x squared to 0, all right, of the natural log of t dt plus the derivative from the lower bound of 0 to the upper bound of 1 over x of the natural log of t dt. So again, because the second fundamental theorem of the calculus requires that one of your bounds is constant, and here both our bounds are variables, we need to sort of split it up into two pieces so that we have a constant on each of the integrals. Because in terms of the curve that you're looking at, in terms of the function you're looking at, you want one of the bounded points to be the same point and then let the other bound approach that. And what you're measuring, again, is the rate of change of that area as the thing slides along. Now, on the right hand side here, we're in good shape because right here we have a lower bound that is what? That's a constant. So that's what we need to use our second fundamental theorem of the calculus. But the other one, kind of like question 14, it's the upper bound that's a constant. And to use the second fundamental theorem of the calculus, we need the lower bound to be the constant. So we're going to use that same trick we used in number 14. We're going to change the sign, and we're going to flip the bounds. So now the 0 will be the lower bound, and the x squared will be the upper bound. And then I'll put in this natural log t dt for that. And as I mentioned, this other one isn't going to change. It's just going to stay like it is because it's in the appropriate form. It's got the lower bound right where we want it. Now, what the second fundamental theorem of the calculus says is we now just substitute the variable bound for the variable in the expression, right? Being careful to remember that you have to do a dt. You got to do a rate of change of that variable bound. And so right here on the left, we're going to have uh, the negative, right, of the natural log of x squared, right? The x squared replaces the variable t, and then you got to have this dt. So you got to measure the rate of change of that bound variable, which I'm going to say pretty obviously is 2x, right? Because uh, using simple power rule, the derivative of x squared is 2x, right? Then we'll do the second one here. So we'll add on, and we're just going to plug in uh, the 1 over x. And now, what's the rate of change of 1 over x? What's the derivative of 1 over x? And you can kind of see it right here. I wrote the 1 over x as x to the minus 1 to make that derivative a little bit easier, right? So that's going to be negative 1, if you want to write it, x to the minus 2 power. All right? Which means what happens? Which means we have negative natural log x squared 2x. I'm just going to leave that one like it is. But then this negative sign right here times that positive right there is going to give you a negative. Okay? And then that's negative x minus 1 times, I'm going to write this, I'm going to put this back, 1 over x squared. And so basically you're done, except that you have to employ a bunch of logarithm rules now at this point. We're going to use a bunch of logarithm rules to get this complete. And the first logarithm rule, I'll put it right over here, it should be familiar from the high school realm. If you have the log of a to the b power, right? What did that tell you? The log of a to the b power. When remember, a logarithm is an exponent for all intents and purposes. And so what do you do when you raise a power to a power? What can I do with that expression? I can replace it with b log a, because when you raise a power to a power, you multiply the powers. So using that idea right here on this natural log x squared, I'm going to get negative 2 natural log x times 2x. And then here, using that same idea, the negative 1 times the negative, that's now going to go back to a positive. Natural log x times 1 over x squared. I suppose really, the first one too, I should have grouped this so that, that's kind of a separate thing. All right. Um, then from there, what we'll what we'll have to remember to do is rearrange things a little bit. You can see that they both have a natural log of x right there. And so we'll factor out that natural log of x. And then I'll put a bracket in here. And when you factor out the natural log of x out of this piece right here, when you pull out that natural log of x, factor that out, you're going to be left with what? Negative 4x. Right? And then when you factor the natural log of x out of here, you're going to have plus 1 over x squared. And we're almost there. The only thing sort of left to do is to combine these two things. You can see through all your choices that they made them all into single fractions. And this has a denominator of x squared, and of course the negative 4x has a denominator of 1. So I'll just go sideways on the page here now. And I'll have natural log of x. And then this negative 4x, I'm going to multiply top and bottom by x squared. So that's going to be negative 4x cubed over x squared. And of course the other term, the 1 over x squared, is already has a denominator of x squared. So that's plus 1. And that's the way that's going to look. Now, from there, it's not exactly the same as the correct answer, but it's pretty close. We have a negative 4x cubed, and we have a plus 1 over an x squared times the natural log of x. And so there's your answer at choice C. So questions 14 and 15, what you really want to focus on, and it's not too bad to do, to execute, but it does help if you understand why you're doing what you're doing. And that's that second fundamental theorem of the calculus. Set it up so you got the derivative of an integral with a lower bound that's a constant and an upper bound that's a variable. Replace the variable in the expression by whatever that bounded variable is, and remember to differentiate that bounded variable, and you should be fine with those. Okay, so I hope those helped, and if you have any questions, by all means get back to me, and we can talk more about this over your break.